So for this loop-de-loop problem, this next one, it is really going to emphasize the conservation of energy. And the conservation of energy is Ui plus Ki is going to be equal to Uf plus Kf. So your potential added with your kinetic in the beginning must equal your potential added with your kinetic at the end. And with this, we have this block. It's starting up here. It's going woo around. And then it is ending at point C. And at point C, we are saying that it has a ending with 4 meters per second at point C. Okay, so that's just to help us out. With that in mind, we're assuming it's starting with 0. It's like at a standstill and it's like stopped, and then it slowly starts to accelerate down this loop. That would mean that your potential energy, if we're looking for the height of h as it's going down the loop, we want this height, will be where we're going to find that h. Because the initial height is what we're looking for, and initial potential is mgh. The kinetic in the beginning, again, it's assuming it's being held here, is 0. So this is going to cancel out, and it will be equal to UF plus KF. All right? So UF will be mg. We're ending at point C, so we'll call that h of c. And that would be plus Kf, which would be 1/2 mv. I'm going to call it c squared because we're at point C. All right. The reason I'm focusing on everything with point C is because we were told it was going 4 meters per second at point C. It also has the height at point C, and it has an angle and all this other stuff that we can deal with around point C. Okay? So with that in mind, notice how all of these have an m. Those are going to cancel out. Goodbye, m. We are looking for the initial height, so let's just divide everything by g. If we divide by g, the g's would cancel out here, and we'd be left with h of c. G's would cancel when we divide by g, plus 1/2, actually I'm just going to write 1 vc squared over 2g. Okay? I don't like that as much. I'm going to write plus 1/2 vc squared over g. I don't know why, but I like they both work. All right, so from there, let's plug in some stuff. What is the height of c? 0.5. Okay, so this is going to be 0.5 for h of c, meters, plus 1/2 vc squared. Well, that would be 4 meters per second squared, divided by gravity, which we're going to call and be lazy and call 10 meters per second squared. That will equal your height initial. Equal the height initial. So let's do some math. If you do all of that math, if you do 4 squared times 1/2 divided by 10 plus 0.15 meters, your initial height will equal 1.3 meters. Okay, so that is part A. Part A is the easier part. Part B, I scratched off. Part C is the main reason for me making this loop-de-loop video. Determine the maximum height above the ground attained by the block after it leaves the track. So this block is, woo, shooting off this track. And we want to know what is the max height on its way down. So it's going to kind of do a parabolic shape. What is that max height? All right. So again, conservation of energy will play in field here, and we will need to deal with it. So we have UA plus KA must be equal to UF plus KF, and the initial is point A. Okay, so I did UA plus KA must equal UF plus KF. We now know the height for the potential energy, but let's figure out what we're going to have to figure out with the final height will relate to the final potential energy, which we don't even have a point here. We're calling it just final, even though it's technically not the final. It's going to go back down to the ground. This block will end up going back to the ground, but we care about when it's at that max height. So with that in mind, we are going to use mgha plus, again, the kinetic energy at point A is 0, will equal mgf plus the kinetic energy at the final. Well, that's the part that I really wanted to deal with. The kinetic energy at the final will be 1/2 mv squared, but that velocity is going to be very confusing because it's going to be 30 degrees influenced. So with that 30-degree influence, the velocity in the vertical direction is not going up or down at that max height. At that max height, it is essentially not going up or down, but it is still going to the left. So at the max height, all the velocity will be in the x direction. There will be none going in the vertical direction. So if you think about that, that means that the x direction will be relating to 30, and it will be the adjacent part with the 30, and that would mean that it is going to be only involving cosine. All right, so let's solve for the velocity before we go any further. Not the velocity, let's solve for the final height. All right, I forgot my h here. Let's solve for the final height. So we have to get this hf by itself. I'm going to move the 1/2 mv squared first. So that would be mg ha minus 1/2 mv final squared will equal mgh final. All right, running out of room. Divide by mg, the m's will cancel all around. So we would divide all of this by g. If we divide this by g and we divide this by g, the g's cancel here. And we have ha minus 1/2 vf squared over g will equal hf. That formula kind of looks like the one we just did. We're going to plug in everything we got, and remember that all of the velocity is in the x direction. So the h of point A, that was what we found in the very beginning, was 1.3. Okay, so HA was the height in the beginning, 1.3 meters. We can plug that in. 1.3 meters minus 1/2 of the velocity, which would be the cosine part only, and we started with 4, so it'd be 4 times cosine of 30 degrees squared, only the x direction, because again, at the max height, it's going to be 0, and then we would end up with A divided by 10 equals HF. All right, so let's do some math with that. You do all that math, and it ends up being 0.7 meters. Sorry for the cut. It was taking a while for me to type it in my calculator. It would be 0.7 meters for your final height. And you may be asking, well, wait a minute, Mr. Sohn, we started with 1.3 meters. How is it only at 0.7 meters? How do we not have any conservation of energy? Well, it's still moving at this point. Remember? So here at the top at 1.3 meters, we were dead, not moving. It was all in potential energy. Here, yeah, we're at the top. It's at the highest potential energy it will ever be, but it's still moving to the right. So it still has some kinetic energy involving it, and therefore at a slightly less height because we have converted some of the potential energy into horizontal movement. All right, that's going to do it for this one. I know it was a long one. I will see y'all in the next one when we do non-conservative forces involving friction. Later. Bye.